Hi, I'm Jaspreet Singh from the Department of Computer Science, Punjabi University, Patiala, and here I'm going to present our work on orthogonal transforms for learning invariant representations in equivariant neural networks. The conventional neural networks are not equivariant or invariant to any of the geometric affine transformations such as rotation, reflection, or scale. However, equivariance or invariance to different transformation is very essential for various computer vision tasks such as recognition, detection, segmentation, etc. Nowadays, the data augmentation approach is most commonly used to learn the geometric behaviors. However, there are many drawbacks of this approach. Equivariance or invariance is not guaranteed. It only learns geometric behaviors globally, and useful network capacity is spent on learning geometric behaviors instead of descriptive representation learning. The hypothesis in the case of equivariant convolutional neural networks is that there is no need to learn the geometric behavior separately. Each layer should achieve equivariance by its own, and equivariance or invariance must be granted throughout the network architecture. The present equivariant convolutional neural networks are based on the group theory, in which each transformation, such as rotation, reflection, or translation, is defined by a group. The one drawback of group convolutional neural networks is that the convolutional and downsampling is performed throughout the network to get the scalar vectors for classification, and fully connected layers are not used for classification because they are neither equivariant nor invariant. In the present work, we proposed the 2D positional encoding scheme between the convolutional and fully connected layers using orthogonal polar harmonic transforms. The PHTs are selected because they are extremely simple to compute and has no numerical instability issues as compared to the orthogonal movements. Most importantly, PHTs are invariant to rotation, reflection, and translation. The PHTs are integrated in the network between the group convolutional and fully connected layers. The process consists of two steps. First, the group transformations are mapped to 2D Euclidean space, and the feature maps are sorted based on their activation energy. Secondly, the PHTs are computed over the feature maps, and the transform coefficients are passed to the fully connected layer for the classification purpose. This is the general diagram of the architecture of equivariant and invariant convolutional neural network. The first part consists of equivariant CNN layers followed by the proposed 2D positional encoding method and fully connected layers. This table shows the test error obtained by PCTs and PCET for different transform orders on a rotated MNIST dataset. The lowest test error is obtained at order 5, and thus for the further experiments we selected transform order 5. This table shows the comparison of test errors obtained by integrating PCETs and PCTs with the group convolutional and partial differential operator based convolutional neural networks and compared with the other state-of-the-art methods. The proposed method obtained lowest test error. Finally, this table shows the comparison with the proposed and other state-of-the-art methods on CIFAR-10 and CIFAR-100 datasets. Again, the proposed method obtains lowest test error. So we have proposed a 2D positional encoding scheme using orthogonal PHTs for equivariant CNNs. The proposed scheme is invariant to global rotation, reflection, and translations. And all group feature maps are utilized for classification. Thank you, and feel free to ask if you have any